primes, a classic problem in computer science that, well, has actually pretty deep implications. Essentially, the whole concept of factorization, taking a number and breaking it up into prime factors, that's always a problem that generates a lot of interest. So today, we're going to take a look at, why exactly this is such a big problem, and we'll be writing some code to help us do this. All this and more in this Random Wednesday episode. Hello and welcome back to another Random Wednesday episode. Just to give you a very quick sort of contents page of what we're going to cover, which hopefully isn't a lot. Firstly, we're going to just talk about primes, what they are, why they are so significant in computer science. Then we'll do 3 pieces of code. Firstly, a simple piece of code to check if a number is prime. So you give it a number, it tells you whether it's prime or not. Once we actually know what primes are, our second piece of code will be basically taking any number and factorizing it down to its primes. So I'll talk about what this means later on. We'll then find that this isn't all that efficient, and what we'll do is we'll go back to the math, we'll inject a few optimizations, and watch as things get much faster. Of course, still not fast enough to have any scary real-world effects. Again, we'll discuss that in the first part. So yeah, that's our roadmap for today. Let's now jump into the first part, which is, well, what the hell are primes anyway? Here's the deal. All this talk about primes and factorizations is all about one operation that looks like this. Essentially, we're talking about what things you can multiply together to get a number. These are what we call its factors. For example, 2 times 3 equals to 6. So what that means is 2 and 3 are the factors of 6. Of course, you could also do 1 times 6 to get 6. So yeah, all the factors of 6 are 1, 2, 3, and 6. A prime number is a special number in that its factors are only 1 in itself. That is, if you take any other number and attempt to divide it by this number, it is not divisible. You will always get a decimal result. So numbers like 5 and 7 are prime. You cannot find any combination of integer factors that, when multiplied together, give you that number itself. Conversely, numbers like 6, numbers like 9, these are not prime, because you can use smaller numbers to multiply together to get the number itself. That is the idea behind what a prime is. So you can think of primes as sort of building blocks, right? These are things that cannot be broken down into smaller parts, so they are sort of complete units. You can put them together to generate bigger numbers. Prime factorization means taking a number and actually breaking it down into the prime numbers that, when multiplied together, makes up that number. In this case, because we specifically say prime factorization, the factors you find must be prime. So, for example, I could say 12 is made up of 4 times 3. That would be a valid factorization, but not a prime factorization. In fact, 4 times 3 will be better off written as 2 times 2 times 3. What we've done is we've broken it down to the most basic building blocks, right? Whereas if we said 4, that is still something that can be constructed out of simpler parts. So that's the idea behind a prime factorization. It's all about taking a number and breaking it down to its prime factors. So that is the math out of the way. But why is this a thing in computing? Well, as it turns out, it is very easy to generate a number by taking 2 very large primes and multiplying it together. However, it's very difficult to actually figure out what those 2 primes were. You see, I'm essentially taking 2 pieces of information and basically combining them together to create one large piece of information. To be able to extract 2 smaller pieces of information out of this one large one, well, I have to actually do a lot of trial and error work before I can get there. And that is why this is used in cryptography, in particular, asymmetric or public key cryptography. Here's the deal. Public key cryptography involves having a public key and a private key. So you publish your public key online, or you keep your private key to yourself. To send you a message, what I had to do was to take my plain text message and encrypt it using your public key. That transforms your message into what we call ciphertext. When you want to actually read the contents, you would put that through your private key, and that allows you to restore the contents of my original message. that is public key cryptography in, just very few words. Of course, there's much more than this, but that's really enough for, the context of primes. If you want to know more, we have talked about this in greater depth in the past, so do check out the card on screen. What's more important here is that this tells us that our public and private key has to be somehow numerically related. As it turns out, the private key are simply the primes used to make up the public key. That is how these two numbers are related. Thanks to the fact that it takes a very long time to factorize a number, it is basically impossible for you to figure out the private key from the public key. So yeah, that is what makes cryptography secure. The fact that it's basically impossible to brute force this within any reasonable amount of time. So alright, with what we have, we're ready to take a look at some code. Now, let's start simple. Let's start by just being able to figure out whether a given number is prime or not. Now, remember, all we're doing here is we're checking the property, right? We're checking to see if it is indeed only divisible by itself and 1. Let's say we're checking the number 7. Well, we're gonna have to check every number between 2 and 6 inclusive. Of course, we don't bother checking 1, we don't bother checking 7, because, well, those have to be divisible, right? Given any number, those two are definitely divisible. In fact, for this, we can use the modulo operator. The modulo operator gives us the remainder of a division, and if two numbers are divisible, you will get a remainder of 0. So what this means is, in this case, we want to check and make sure that no division operation gives us a remainder of 0. In the case of 7, this is true. 7 cannot divide cleanly by any number between 2 and 6, and therefore, we know that 7 is prime. Conversely, if we tried a number like 8, well, in fact, the moment we moved on to 2, we realized that, hey, we could actually divide it cleanly by 2, right? We would get 4. And what this tells us is, well, 8 is definitely not a prime number. In fact, I don't even have to check any of the further items. While I could go and divide it against everything between 2 and 7 in this case, I don't have to. Because it already fails on a division by 2, there is nothing else I need to do. Nothing can make it prime again because it's already non-prime. So yeah, I can stop. I can immediately say, yep, 8 is not prime, and I'm done. We are now all ready to build our prime test function. So, well, we are of course writing Python code, right? So, define prime test, and we'll take in a parameter x. X shall be the number in which we will be testing to see if it's prime or not. As discussed previously, we will be trying to, well, divide x against every value between 2 and x minus 1, right? So we'll write a for loop, we'll generate a divisor within the range of 2, right? So 2 is inclusive to x. So in Python, when you write a range object like this, what happens is it will generate for you all the numbers within this range, 2 inclusive, x exclusive. So it stops at x minus 1. So yeah, this is exactly the behavior we need. So given the divisor, all we need to do now is to test x against the divisor. I would say if x, and for this we'll use the modulo operator. So if x is actually divisible, then we'll get a remainder of 0, right? So by definition, that's what, having a number that is divisible actually means. Now, the moment we encounter this, what this tells us is that x is non-prime, because x is not supposed to be divisible by anything within this range. If you see that it actually is, then x cannot be prime. Remember, the moment any factor is divisible, we're done. So in this context, we can simply return false. We're done. We don't have to think about anything else, right? Because we're sure that x cannot be prime. Conversely, if the entire loop actually runs to completion, right, we do every single division, and we realize that, hey, none of these numbers are actually divisible. This tells us that x is indeed prime. So outside of the loop, right, when the loop actually finishes up, we can return true. We now know that since nothing is divisible except 1 in itself, x must be a prime number. Let's test this out, right? Just have a few simple cases. Of course, we know that, say, 7 is a prime. So if I try to print prime tests of 7. This should give me true, right? Conversely, something like, say, prime test of 10, this will of course be false. These are the results we get, which tells us that, well, our function is indeed working correctly. And there you go. We now have code that helps us test if a number is prime. Now, our goal at the end of the day is to do factorization. So what that means is, well, we need to go one step further. Now, given a number, we're going to have to try and divide it by increasing prime numbers until at the end of the day, well, we actually get all the factors out. Before we delve into the code itself, let's try and better understand how it's going to work. Here's the idea. You start off with an input value. This is the value you want to factorize, of course. We're going to essentially generate primes. We'll start with the smallest prime, 2, and we'll see if it's divisible or not. If it's not divisible, that's fine. We'll just keep going on, right? We'll just keep trying prime after prime after prime until we end up at one that is actually divisible. Here's the critical part. If it is divisible, we perform the division and we basically reduce our input number down. Then we try again using the same prime. If it's no longer divisible, we continue our process to find the next prime. In this case, 11 is divisible, so we'll do the same thing. We'll continue diminishing our prime number. Now, don't forget, we need to test again on the same prime, and for a good reason. In this case, 143 is still divisible by 11, and so we reduce its value some more. Of course, this is no longer divisible, we'll move on to our last prime, right? That's 13, that's divisible, and we end up with 1. This is when the entire process ends. Our input number will be diminished as we move down our list of primes, and we only stop when the output becomes 1. The reason why we want to do that is because, well, now we can say what are the prime factors of this number. The prime factors are 7, 2 instances of 11, which we can express as 11 to the power of 2, and 13. So this is how we're going to approach prime factorization in general. We'll take the number, we'll keep on reducing it down until it gets to 1. So it's time to factorize. Right, so we'll give it a number, again let's call this x, and yeah, we will attempt to factorize the number. Now, you've already seen how this is supposed to work. We're going to have to start off by generating our prime numbers, right, and we'll keep performing divisions until our number, the original x, goes down to 1. So we'll say while x is greater than 1, right, that means we have to perform more and more divisions. We'll basically start off by generating a prime number that we can use to perform our division. Because this is a while loop, we're gonna have to keep track of our divisor separately. So let's start off with a divisor of 2. So I would say if prime test on the divisor, right, we're just testing to make sure it is prime. So yeah, this will check to see if it's prime, right? In fact, you know what, to make this more readable, let's change this to is prime. So hopefully this line becomes a bit more readable. If the divisor is prime, then continue. Alright, so we'll have a else divisor plus equals to 1. Right, so as this loop runs, what's going to happen is, well, we're going to keep counting up with the divisor. So alright, we have a prime divisor now. We'll attempt to divide x by the divisor. So if x modulo the divisor, that gives us 0. That means that the divisor is indeed one of the factors. So we'll take x and we'll divide it by the divisor, right? We'll actually store the result back in x. So this diminishes the value of x. Conversely, if this couldn't be divided, then we're done, right? We have to move on to the next divisor. This divisor isn't going to do anything else for us. Remember, if it is divisible, we're not done. We're going to have to loop back around and try and use the same divisor again, just in case you could use the same divisor multiple times. So essentially, our factorization code looks something like this. But we need one more step, of course, and that is to keep track of what all the prime factors actually are. Now, I'm going to keep things very simple here, right? We're just going to have a list like that containing prime factors, and every time I discover a prime factor, I'll simply append that value into our prime factors list, like so. At the end of the day, right, this is going to keep running, x is going to get diminished, and eventually x is going to become 1. When x becomes 1, we'll jump out, we'll exit from here, and we'll simply return that entire list, which contains, of course, all our prime factors. Let me scroll this up so you can see the entire function. And there you go. This is the simplest, most basic way of generating a full list of prime factors. That is the idea. Let's now write some code to test it out. Let's try something like this. We'll try and factorize 1001. This will give us a list of all the factors that can actually generate this. Right, so we're going to run it, and we'll see that our factors are 7, 11, and 13. Just to prove that this is indeed correct, we'll do just that. We'll take 7, multiply by 11, multiply by 13. There you go, 1001. Awesome! We now have code that will help us perform prime factorization. However, look what happens. If I give it a slightly larger number, it trips right up. It takes a lot of time and it's not really able to, terminate within a reasonable amount of time. So that's not great. Now, this is partly because, factorizing primes is a difficult process. That's unfortunately the truth, we can't change that. But what we can change is we can actually improve on how we approach the problem. Right now, what we are doing is actually quite redundant. What we're going to do is we're going to go back to the math, we're going to take a look at some things that we are not doing quite right yet, and then we'll go and implement it into our code. And we'll see, that things are actually picking up. They are going to be slightly faster, but not fast enough to break encryption, of course. Let's take a look. Now, as we continue into the next part, we're going to start talking about efficiency. To do that, we'll like to see some numbers in terms of how long things actually take. So what I'm going to do is I'm going to actually import a library from Python itself, It's called datetime, and the idea is we're going to actually time it. We'll take a snapshot of the time before we run the factorize function, and we'll take a snapshot again after. By making a subtraction of these two times, I can actually tell, how long the operation has actually taken. So here's how we're going to do it. We're going to say start time equals to datetime.now. So this actually creates a date object that represents the current point in time. Then after the function has actually been run, we can calculate a time difference by taking the current time. So when I call dt.now, I'm talking about the time now after the function has run, and I'll take a subtraction from the start time. Of course, these two nows would have happened at slightly different points in time, So this will give us the difference in time. So yeah, at the end of the day, what we can do is we can print, and we can sort of give a report on how long this operation has taken. So yeah, we'll say something like time taken is, we'll create a gap here to use with a formatting string. This is just how, we substitute values in Python. We'll take time diff dot total seconds. So this is a function to turn this object into just a number, which is the total number of seconds. So yeah, let's do that, Let's, have a unit so we know it's seconds. What we're going to do is we're just going to add a few more ones here, And now let's try running our code. As you can see, there is a noticeable delay. And thanks to the fact that we have actually used our timing functions to calculate how long that delay is, we know that it took about 0.8 seconds, almost 0.9 seconds. Of course, the actual value of the time itself doesn't say a lot. All it says is that is how long it takes on my computer. If you use a newer, different computer, you're going to get different times, but this number is useful when we compare it against the more efficient method we're going to use next, which, now that we've mentioned it, let's take a look at that. Our current approach basically divides our number by everything between 1 and itself exclusive, so everything in between. But as it turns out, we are doing quite a fair bit of redundant work here. There are two optimizations that we can do that will actually reduce on the amount of trial and error we have to do. Now, let's say I'm going to try and check to see if a particular number is prime, So I'm going to have to divide it by, all the numbers between 1 and that number. And let's say now I'm trying to divide it by 2 and it fails, right? What that means is, well, I have a remainder when I divide that value by 2. By this same logic, every factor of 2 down the line, well, I don't actually have to think about it. If I can't divide something by 2, no way can I divide it by 4 or 6 or 8 or so on. Same deal, right? If I can't divide something by 3, I don't have to think about dividing it by 6 or 9 or 12 or so on. In fact, every time you check your number against the prime number, you've implicitly also checked it against every composite that is non-prime number that contains that factor. So, in fact, instead of dividing a number by everything between 1 and n, you can just divide it by every prime number between 1 and n. Non-primes have implicitly already been checked. You don't have to bother with those. This is great because this actually cuts down on a lot of the checking we have to do. And here's another. Why do we need to check everything all the way until the end? In fact, all we need to do is to check everything not up to n itself, but just up to the square root of n. So, in order to understand why we can actually stop checking at the square root of the number, well, we need to look at a little bit of math. Let's say a value a is non-prime. Because it is non-prime, it has to be made up of at least 2 prime factors, n and m. For the sake of simplicity, let's just assume there are 2. The reason why we can stop at the square root is if one of the factors is greater than the square root, the other factor must be smaller. What that means is if we stop at the square root, we will still be able to detect that there is a factor. As long as we know of its presence, we can already say a is non-prime. Clearly, this is not a statement that I can just state and get away with, so let's try and prove it by doing a proof by contradiction. Let's say that both n and m, right, both factors are greater than the square root of a. Of course, if that's the case, we could not stop at the square root. Now, assuming that this is the case, what we can do is we can attempt to multiply n and m. Since we know that both those terms are greater than the square root of a, then what happens is, well, when we multiply them together, we will get something greater than a. Clearly, that's not going to work. That is a contradiction of our original statement, where n times m must give us a. Therefore, we can never have a situation in which both n and m are greater than the square root of a. If one value is greater than the square root, the other value must be smaller. And what that means is, well, if we're looking to see if a is prime or not, we can stop checking at the square root. Remember, if it's a big number, taking the square root makes it much smaller. So yeah, this is great. I've basically reduced my search space by a very large order of magnitude. Let's go ahead and implement these changes into our code and let's see how much faster things become. Now, the first one of the two optimizations could be a little bit challenging. I'm talking about the one in which we only need to divide against primes. To do that, you're gonna have to assume that you already have, well, all the previous primes in place. And if we're arbitrarily checking prime numbers, we don't. We would have to generate that list. Thankfully, because we are doing factorize, we are generating the primes sequentially, one by one. Now, I'm going to cheat a little by creating a global variable. This basically is a list of all the prime numbers we've encountered up to this point. Essentially, every single time this function encounters an actual prime number, so that is where we actually, pop over to this part, we would append the number to the primes list. As a Python convention for a function to modify a global variable, we would have to say global primes. So this is, just Python convention. So now what we need to do is we need to, instead of looping through a whole range of values like this, we simply loop through all the primes that we have. So for divisor in primes, and then we can keep testing this as usual. So this is the first half of our optimizations. Let's do our next one. As we go through the primes, we will eventually encounter a prime that is greater than the square root of x. So that means we've hit our stopping point. Now, in order to compute our stopping point, we need to perform the square root operation. So we import the Python math library to help us with that. If the current divisor we are looking at, is greater than the square root of x. This means I'm done. I don't have to do any more computation. If I've lasted this long, x must be prime. So we simply break out from this loop, right? That will allow us to hit these two lines, right? It'll append a new prime, and we're done. Now, earlier on, we did this example, and we noted that it took about 0.86 seconds. Let's now try this again and see how much more efficient things have become. As you can see, this is a huge improvement. 0.03 seconds. That is a huge difference. Now, ladies and gentlemen, as usual, whenever we do any coding video, all the code pages will of course be in the video description for you to download. And today I'm throwing in something a little bit extra, right? What I have here is, a slightly longer piece of code that uses more Python-like features. Essentially, this works something like this. When you run this piece of code, you'll get to enter the number yourself, right? And it will sort of crunch through it, and it'll display the answer in a nicer manner. It'll also, present the timings and everything, again, in a nicer manner. So yeah, this is sort of the more friendly way, right, of using, the same algorithm that even shows things as powers, so it'll figure out the actual power of all the factors. So yeah, if you like, right, you can actually check out this piece of code. It just takes the same thing a little bit further, that's all. So yeah, this is even designed to show you the status of the program as it is running, so it shows you which prime it is using to perform the factorization at that present moment. Of course, if it takes too long, you can also kill off the program by pressing Ctrl+C. When you do that, it even gives you, the answer based on what it has at that point. Now, clearly this number is a little bit crazy, right? So it didn't manage to factorize it at all. So let's say if I were to change up the same number to something that, feels a little bit more normal, maybe we'll see that, right? It has factorized out a certain part of it, but there is still an unfactorized portion. So this one is essentially what is left, right? Remember, every operation diminishes the number, so this is what is left behind, which is what the program hasn't yet had a chance to actually factorize, right? Based on the largest prime it has seen up to that point. There are actually two versions of this code available. There is a non-extended version which essentially uses the original algorithm, the one without the optimizations in the prime finding part. So yeah, you can compare and contrast the output given by these two functions to see the difference in terms of the time it actually takes. So yeah, just a little bonus for you. Of course, the code that we've written for this episode will also be available. You will find the download link in the video description. And there you have it. That is essentially figuring out prime factorization. We have looked at how and why it's a hard problem and why it needs to stay a hard problem for a lot of things to continue working. We've then moved on to actually building it ourselves using Python code. And yeah, we've seen that, that's essentially how it works. We've seen where the pitfalls are, we've seen how we can make things better. So, that is essentially all I have for you on the topic of prime factorization. I hope this video has been useful to you. But yeah, that's it. Until next time, you're watching 0612 TV with NERDfirst.net. Thank you very much for watching. If you like my work and are feeling generous, you can shoot me a one-time donation on PayPal or sign up for a recurring one on Patreon. Of course, you can simply like, comment, and subscribe. You know the deal. For more videos, links to my channel and a related playlist are on screen. Thank you for your support.